So let me introduce him to you. Huyên is a full professor at École Polytechnique, which is also my alma mater in France. He's the current president of the Bachelier Finance Society. Huyên is one of the leading mathematicians at the intersection of mathematical finance, stochastic control, and machine learning. His research spans portfolio optimization, mean field systems, deep learning for high-dimensional PDEs, partial differential equations, and generative modeling, areas he has shaped through decades of influential work and extensive publication record. He's a laureate of the prestigious Louis Bachelier Prize from the Academy des Sciences. He also serves as editor-in-chief of the Siam Journal of Control Optimization and has delivered keynote lectures at venues ranging from the ACM International Conference on AI in Finance to the National University of Singapore's Quantitative Finance Conference. So please join me to welcome Professor Huyên. So the topic today will be about the bridging Schrödinger and Bass for generative diffusion modeling. So it'll be a very interesting talk and a very innovative technique for generative AI. Okay, so thank you, Huyên. You can start now.
Okay, so thank you, Min, for this nice introduction, for the invitation. So I think it's my second time to this AI for Good talk. So I think I remember last time was 3 years ago, I think, right?
Yes.
So this work is this work is somewhat in the continuation of a project that I started about 3 years ago, and today I would like to present, in fact, a probabilistic perspective on generative AI. So the main idea is simple. So generating data can be viewed in general as transporting randomness. And in modern generative AI, we often start from simple noise, and then you transform it into structured data. So for example, image, time series, financial scenario, or scientific simulation. But today, I want to focus on a slightly different questions. So the question is, can generative AI learn not only what to generate, but also how uncertain the generation process should be? So this leads to what we call a Schrödinger-Bass Bridge. But first, let me Let me first acknowledge the collaborators behind the different part of this project. So this project is based, in fact, on several joint works. So with Alexandre Alouadi, who is currently a PhD student of mine, working also at the BNP Paribas. Mohamed Amdouche, a former PhD student, so now working in the hedge fund Cube. Pierre-Henri Labordère, so senior researcher at Cube. Céliane Marsala, who is in fact a master student and who collaborated within this project as part of his internship as BNP. So Othman Maza, who is a former postdoc at my previous university. Grégoire Lepère, who is the senior advisor at BNP Paribas. And Nizar Touzi, who is now professor at NYU Tandun. And unlike later in the talk, so the face that you see here are real. So this project combines several viewpoints, so optimal transport, stochastic control, generative modeling, and financial time series. But I will try to be the less technical possible and rather mainly convey the main idea. So let me now explain the big pictures. So the common picture in generative AI is that you start from a simple randomness, for example, a Gaussian distribution, and then you gradually transform this randomness into something structured. And eventually, at the terminal at the final horizon, okay, you obtain samples that look like the target distribution, which is typically a complex unknown distribution. So for example, here, distribution of human face. And so the important word here is gradually, in the sense that the transformation is not a single jump, but it is a path. So this is so we are not just learning a function that maps the noise to the data, but in fact we are rather learning a stochastic evolution. Okay, and so this leads to a useful distinction. So versus you generate by a map versus generating by a movie, in fact. So in classical generative models, for example, GANs, so for generative adversarial networks, so you often learn a static map. So you start from a noise, then you apply a trained neural network, and then you obtain data. But in modern diffusion type model, it's rather different. So in fact, you learn trajectory, and then the sample is progressively refined. So it's in the sense that now a generation becomes a movie rather than a snapshot. So this is one of the reasons why diffusion models are so powerful. So they break a difficult transformation into many small stochastic steps. So mathematically, this leads to stochastic dynamics. So let me show you. Yeah, let me show you, in fact, the mathematical tool behind the stochastic evolution. So here you see the evolution of a diffusion process. So the first term here is a drift. So it tells you how the particles move on average. So in machine learning language, this is a learned direction field. The second term is volatility. So it controls how much randomness is injected into the trajectory. So in this view, a generative model learns a stochastic dynamical system that transports a simple distribution, mu0, into a complex data distribution, mu capital T. But in fact, most diffusion models, like a score-based diffusion model, for example, or stochastic interpolation, mainly learn the drift, while the noise level or the volatility is usually fixed in advance. And so the question that we're asking in this work, in this talk, is can we also learn the volatility from the data? So to see where this question comes from, so let me first recall or introduce the Schrödinger Bridge. So the Schrödinger Bridge is in fact a classical and beautiful problem in probability theory. And so the problem is the following. So among all random evolution connecting two distributions, so you want to select the one that perturbs the Brownian motion as little as possible. Okay, so this is mathematically formalized as this control problem. And so you can think as the Schrödinger Bridge as a most likely stochastic path between two data clouds. So you prescribe where the process starts and where it ends, and you choose in some point the most economical stochastic evolution between these two clouds. So this is exactly the kind of object we need in generative modeling. So a stochastic process that starts from noise and ends at the data distribution. And so here the output is a drift field, okay, the drift of your Schrödinger Bridge, which is in fact expressed as a score. So this is making in fact the connection with a score-based diffusion model, and which tells you how particle has to move. And in fact, this theory of Schrödinger Bridge gives a practical generative algorithm. And so in practice, okay, you will learn the bridge from examples. So you start with sample from the noise distribution and sample from the target distribution. Then you will learn the score, so in other words, the direction field. Then you simulate your random path. And finally, okay, you generate new samples. And now modern solvers make this scalable in high dimension, in particular for generating an image of a human face or whatever. And but there is a limitation in this theory and this algorithm is that the random noise level in this Schrödinger bridge theory is fixed. So it's fixed to usually a constant. But in many domains, uncertainty is not something you would like to fix. It is rather something that you would like to learn. Okay, and so this motivates why we want to go beyond the theory of Schrödinger bridge. Okay, in the sense that in many domains, as I said, uncertainty is not a nuisance. It is in fact a signal. For example, in a financial market, volatility is part of the data. Often volatility tells you more about risk than returns themselves. In science and health, variability may encode hidden mechanisms, and a patient trajectory, for example, is not deterministic. In AI safety, a model should represent ambiguity, not hide it. So overconfident synthetic data can be misleading. And so in this work, in this project, we are interested by formulating a framework, okay, that keeps the tractability of Schrödinger bridge, but at the same time learn also volatility. Okay, and so this is the goal of the Schrödinger-Bass Bridge, where you learn both direction and uncertainty. Okay, so on the one hand, the Schrödinger bridge theory, and on the other hand, the Bass martingale transport theory, which look at pure martingale process where you only control the volatility. And now let me make this distinction between drift and volatility more explicit. So as I said, drift, okay, tells you how particles tend to move, while volatility tells you how much randomness is injected. And so a model that learns only drift can learn only the average direction of data transformation. But a model that also learns volatility can represent diversity, ambiguity, stochastic volatility, and multiple possible features. And so, in fact, Schrödinger-Bass Bridge will learn both. So now, let me write the optimization problem behind this idea. So this is the main mathematical slide of this talk, the main mathematical formula. So given a fixed initial distribution and target distribution mu0 and mu capital T, okay, we want to choose a stochastic process with both drift and volatility, which minimize some quadratic cost. So this quadratic cost consists into two terms. So the first term penalizes the drift, while the second terms penalize deviation of the volatility from the identity. And so you have some parameter beta which controls this trade-off. So for example, when beta is very small, so when it goes to, for example, it goes to 0, this means that in fact the model is allowed only to learn the volatility. So you, in fact, it's like you constrain the drift alpha to be equal to 0. And so in this case, okay, this moves us towards the Bass martingale transport theory. On the opposite side, when beta is large and goes to infinity, okay, this means that in this case, you want to keep the volatility close to identity, and then you recover the Schrödinger bridge. Therefore, the Schrödinger-Bass Bridge continuously interpolate between these two classical constructions. On the one hand, the Schrödinger bridge, and on the other hand, the Bass transport. And what is remarkable, in fact, is that this interpolation still have a tractable structure. And let me now give you the solution, so called the Schrödinger-Bass Bridge system, okay, in one picture, in one diagram, which in fact sum up the whole theory. So you start from your original noise distribution. You apply a Bass type map, okay, to move your noise into a transform noise. Then in this transform space, you construct a Schrödinger bridge by learning the corresponding score drift. And then, so this means that this bridge learns the direction of the transport. And at the end, okay, you apply the inverse Bass map to return to the original data space. And this formula, okay, says that the final process, xt, okay, is obtained from the bridge process yt plus a correction involving the score. Okay, and so the mathematical theorem behind this slide is that the Schrödinger Bass Bridge can be viewed as a Bass transport of a Schrödinger bridge. So in other words, so the bridge learns the direction and the Bass correction learns the uncertainty. And what is nice is that
I have questions maybe on the, so this diagram, is it that you go through that loop at every time step, or is it from only at the beginning?
Yeah, you iterate. You have to iterate,
right? Yes.
Because the Bass map you don't know.
Yeah.
So you have to iterate to learn the Bass map. So in fact, you iterate this loop to learn the Bass map. Yeah. Indeed. Yes, good point. And now, in fact, this loop leads to a practical algorithm. And in fact, this algorithm follows the structure of the theorem. So you start from your input data. You first learn the Schrödinger bridge, and then you apply a Bass type transport correction. And indeed, to learn this Bass type correction, you have to iterate along this loop. And then finally, you generate new sample. And so the final output is a generative model, okay, with learned drift and learned volatility. Okay, so this is the theory. And so now let us now look at some experiments, okay, about how we can implement this theory and algorithm. And I will start with a standard two-dimensional benchmark, okay, which has been introduced by the Mila group in Montreal of Yoshua Benjo. And so here we transport a simple distribution, so in blue, mu0, toward a more complex target distribution in orange, mu capital T. So these distributions are distribution of moons, mixtures of Gaussian and multimodal shapes. And so here you see for different data sets, okay, the transformation when we vary, okay, the parameter beta of the Schrödinger-Bass Bridge theory. And on the right, okay, what we plot is a Wasserstein distance, which measure how close the generated distribution is to the target distribution for a different value of beta. So we look at what is the value of beta which minimizes this Wasserstein distance. And so you see that we observe that learning volatility improves the quality of the transport, and that there is a useful trade-off, okay, controlled by this fine-tuning parameter beta. So the next slide summarizes this quantitatively. So here we compare the Schrödinger-Bass Bridge with several benchmarks, so different type of generative model that has been previously performed in the literature. And so here I give the best, the strong baseline. And so lower Wasserstein distance means that the generated samples better match the target distribution. And so you see that across all these three benchmarks, okay, the SBB it gives the best performance. Okay, so now let us move from this toy distribution to image generation. Okay, so here the task, okay, is to transform adult face into childlike face while preserving identity. And so here, for example, you start from the face of a woman adult, so x0. So you apply the Bass map, then you diffuse, okay, according to the Schrödinger Bridge, and then you apply the inverse map, okay, to obtain a girl childlike face, okay, while preserving the identity. And so what is important here is that you see the gradual transformation. And so you see that this model change age-related feature while preserving identity. So this illustrates the advantage of dynamic transport. So we do not simply jump from one image to another, but we construct an interpretable path. We can also, in fact, start directly from noise. So here the model starts from pure noise, and then it generates sample from three sample from a child. Okay, and you see that the average generated age is much closer to the target, and the proportion of generated children, okay, increase substantially compared to, for example, compared to the Schrödinger Bridge, the pure Schrödinger Bridge. So identity similarity remains reasonably high, which suggests that the model is not simply distorting the samples arbitrarily. And learning volatility improves the match to the target distribution. Okay, so here, okay, this is a theory for image. But what is in fact more challenging and even harder is the case of time series. Okay, so now we want to go beyond image, and we want to extend to the generation of time series. A time series, in fact, is not just a distribution of points. Okay, it's in fact a distribution of paths, of trajectory. And in a time series, ordering matters, so the causality of the time series matters, the correlation matters, the volatility clustering matters, and two models can have the same marginal distribution at each time, but completely different dynamic. So for time series, okay, we need to synthesize realistic trajectory, not just realistic snapshots. So this leads to the time series version of the Schrödinger-Bass Bridge, okay, that we call Schrödinger-Bass Bridge for time series. So this theory, in fact, extends the same ideas sequentially to time series. So at each time, the model conditions on the past trajectory, and it then learns the conditional distribution of the next step. So yeah, then you repeat this step, okay, at each observation time, okay, and then you will learn the conditional distribution of the next step. And repeating this step will generate a full synthetic trajectory. So by doing this, okay, you will preserve the temporal dependence and allow the models to learn stochastic volatility effect. Okay, now let us test this in a financial context. Okay, so compared to image, financial markets are very difficult because, in fact, uncertainty itself evolves over time. So period of calm can alternate with period of turbulence, and correlation between source of randomness also change. And so the Heston model is a classical stochastic volatility model. So the first equation, dx, okay, is a model for the asset price. The second equation, okay, models volatility itself as a random process. So you see that volatility is no longer constant. It fluctuates over time. And the parameter rho here, okay, measures the correlation between the noise driving the price and the noise driving the volatility. And so this is important in financial markets because in financial market, volatility and returns are often statistically linked. And so this is one of the stylized facts that make financial time series difficult to model. And so the experiment that we are performed is the following. So now if we train a generative model on many samples of Heston trajectory, so where we sample by varying the parameters, because in practice, the parameters of the Heston model are not constant, then the question is, can we generate new trajectory from which we can recover the original hidden parameters? And so in blue, you see the true data distribution of the parameter of the vol of Xi. And here on the right for the distribution of the correlation parameters. Orange is the previous Schrödinger Bridge time series model. Okay, so the model where you fix the volatility. While in green, okay, you see the distribution obtained from the Schrödinger-Bass Bridge time series. And so you see that the Schrödinger-Bass Bridge time series better captures stochastic volatility and correlation than the fixed volatility bridge theory in Schrödinger Bridge. So the key point is that okay, the Schrödinger-Bass Bridge theory better recovers the distribution of the volatility and of the correlation parameters. So this experiment shows you why learning volatility matters, okay, to generate realistic financial dynamics, okay, so the model also need to learn how uncertainty itself evolves. So the next question, okay, is whether this helps downstream machine learning tasks. So, as you know, financial forecasting is known to be difficult because the signal-to-noise ratio is extremely small. In general, in return, you have more noise than signal. And unlike image generation, we do not have millions of independent samples of market history. Okay, you essentially observe, in fact, one historical observation of the market. So the idea is to therefore to generate a synthetic trajectory that could enrich the training distribution. So we start from historical S&P 500 returns. Then we generate a synthetic trajectory using the Schrödinger-Bass Bridge time series model. Then we augment the training data and we train a forecasting model. and then we evaluate the prediction and trading performance. And so data, but at the end, okay, data augmentation will be helpful only if the synthetic data can preserve the right temporal structure. So simply adding Gaussian noise is not enough. And so, okay, so the question is, can synthetic trajectory improve real-world forecasting? So in this slide, okay, we compare three regimes. So the first regime is real data plus naive Gaussian noise. The second is only real data. And the third is real data that we augment with a synthetic Schrödinger-Bass Bridge time series trajectory. So in this table, so in this classification metric, the accuracy measure whether the model correctly predicts the direction of the next return. So positive or negative. So if the next return is positive or negative. And the log loss measure probabilistic calibration. So it asks not only whether the model is right, but whether the confidence is meaningful. For the financial metrics, so the average daily returns measure the mean profit of a simple strategy. So the standard deviation measures the risk, and the Sharpe ratio measures the return adjusted by the risk. So in finance, generating return is easy, but generating stable return is difficult. So you see that we observe improvement in accuracy, log loss, average daily return, and Sharpe ratio when augmented with synthetic Schrödinger-Bass Bridge time series. Okay, so the important point is that Schrödinger-Bass Bridge time series does better than naive noise augmentation.
I have a question on that table.
Yes.
Your Sharpe ratio looks a bit high, even in the real case. Why is that?
Well, so because you mean compared to the real noise? Yes, so indeed. So, yeah. So what we show here is that, so in fact, of course, we add a lot of synthetic data because we are not limited in the simulation of synthetic data. So we can train with a lot of synthetic data. And in fact, using synthetic data, we in fact are able to capture, compared to just adding noise, we are able to compare some signal. This is the main point. Using synthetic data, we can remove noise and capture the signal. This explains why we can improve, rather significantly the Sharpe ratio.
Okay. I mean, I was simply because stock market is very difficult to forecast. So using real data, only you expect the Sharpe ratio to be much lower than 1. But
yes.
Yeah.
So okay, I'm not saying that's okay. This suggests, in fact, that here synthetic trajectory are not merely adding randomness. Okay, we are able to. They are also useful to capture a predictive structure. In fact.
And the real only, does it mean, is it like some kind of Monte Carlo simulation, or you resample the real data, or it's just using the historical path?
You mean in the third regime?
No, in the second regime, we say real only.
Yeah, no Monte Carlo, just the historical path. Just the historical path. No, we do not use a bootstrap or this kind of.
Okay. It could be also a benchmark, right? So bootstrap could be a benchmark also as a comparison.
Yes, it could be also. But I don't think it will. We also tested, but it doesn't really. So it will improve slightly better, but not. Not comparable to using synthetic data.
Okay. Are you familiar with the research? I haven't read his paper in detail, but Charles Albert, right? Charles Albert Leal, I think he made a presentation of, try to generate like time series data in finance. He said it was impossible. Was there something?
Yes, I know.
Sense, yeah.
I know. Yes. I know. We have a lot of discussion on this. Okay.
Okay.
Okay, so the next slide shows the same effect, but now dynamically through time. So this slide shows a cumulative performance through time. So the green curve corresponds to the model trained with Schrödinger-Bass Bridge, augmented data. And the other curve corresponds to baseline trained without the synthetic augmentation. And so what matters here is not one isolated prediction. What matters is robustness across a different market regime. And so the right panel shows the excess return relative to the benchmark. And so you see that the SBBTS based model remains stronger over the test period. Of course, the goal here is not to claim that this is a production trading strategy. So the goal is rather to test whether synthetic probabilistic trajectory improve downstream learning. And so the results suggest that they do. Okay, so now because this is a AI for good talk, so let me now step back and connect this to the broader AI for good perspective, so beyond finance. So why does learning uncertainty matter for AI for good? So a generative model that produce realistic sample but unrealistic uncertainty can become dangerously misleading. So for example, in healthcare, synthetic trajectory could help train model for rare disease or underrepresented population while protecting privacy. So in climate and energy, so we need plausible extreme event scenario, not just average forecast. And in finance and risk management, robust decision require understanding uncertainty and stress scenarios. And so across this example, uncertainty is not just a nuisance to remove, it is information that must be modeled faithfully. And so reliable generative AI should produce not only realistic sample, but also realistic uncertainty. And so this is why uncertainty is essential for trustworthy AI. And so let me finish with the main takeaways of this work and this talk. And so I would like to conclude with 4 messages. So first, generative AI can be viewed as a stochastic transport. Second, Schrödinger Bridge learn a direction field, but usually keep the noise fixed. Third, Schrödinger-Bass Bridge learn both drift and volatility. And fourth, learning uncertainty improves sample quality and helps time series synthesis. And so the final question is, can generative AI learn not only what happens, but also how uncertain it is? So this is, in fact, the central question of this talk. So in mathematical terms, it means learning not only the drift of the stochastic process, but also its volatility. So in other words, can AI generate not only a realistic world, but also realistic uncertainty? And to conclude, let me just give the reference underlying this talk. So the first talk is in fact provides a theory between behind this Schrödinger-Bass Bridge problem. The second paper is it gives application to algorithm for image generation. The third paper here is the extension or the version to application to time series, in particular to financial time series. And so the first word is when I started to work on this domain. So it's is when I work on Schrödinger-Bass Bridge, only on Schrödinger Bridge theory. So this is a talk that I presented 3 years ago, and which is now appeared in the Journal of Machine Learning Research. And so I think I am on time now, and I will stop
Yes,
here.
perfect.
And
Perfect.
so
We have
thank you
plenty of
for your
time.
attention.
Thank you very much. So please, I mean, the audience, if you have any questions for Huyên, raise your hand, and I'll unmute you, and you can ask questions. So what you're thinking of for questions? Yeah. So maybe while you're thinking of questions, maybe I can ask a couple.
Right.
The first one is in your paper you talk about about the theory of convergence, right? So you see that some the algorithm you talk about inner loop and outer loop when you run the algorithm. So one is proven there's a convergence in the inner loop, but the outer loop is still a bit heuristic or empirical. But you have high confidence that it's working just a few iterations you'll get to uncover the parameters. So is the next step to try to prove that there's convergence too, or it doesn't really matter?
Yes, so this is the loop is here. So indeed, so we do not have any, for the moment, we do not have any convergence result about the algorithm. So we, in practice, so we have iterate this loop to learn the map. In practice, we use only 5 iterations. And after 5 iterations, we observe that we already learned very well the score and the volatility. And we see that, yes, the training loss is already converging to 0. But it's not a theorem. So it's a practical implementation, which means that we don't need to iterate a lot. In practice, it is sufficient, okay, to iterate this loop, maybe just with only 5 iterations.
Okay. So maybe
But of course, the next step. So the next step. So we plan to put some student or postdoc is to study, to have more comprehensive and convergent analysis of the algorithm behind this Schrödinger-Bass Bridge theory.
Okay.
But probably this is a very, very difficult task, because even for the case of the Schrödinger Bridge theory, so related to the single algorithm, there are rather few convergent results. So I think it's a difficult. It is a challenging problem.
Okay. Also, another question on your model. So that beta coefficient is fixed. Are you thinking of extension where beta could be like could be moving, or there could be a few
Yes, good
variation
point.
beta?
So already there is so for the moment here, indeed, beta is fixed, and it is tuned. So we test different value of beta, and then we see which one gives the best result. So in practice, we fix beta to maybe 150 or 100. So probably the theory could be, I think, easily extended to the case where beta is deterministic. So in this case, I think it should be possible to extend this theory. So if we want to control also beta, probably it is another theory, another story, much more harder. But yes, probably it's a good way to have a way how to choose, I say, in optimal ways the parameter beta.
Okay. Okay. My last question is we're getting some small related to this paper, but now we have like no, there's I think yesterday or 2 days ago there were OpenAI published a paper about applying mathematics to find of these they're trying to resolve some of these those problems. So use AI in math and so on. So do you follow that, and are you applying this in your own work, or do the students start to use these tools? No,
So
ChatGPT, so
yeah,
start
of
to
course
do
now,
math.
yes, of course now we are in the area where we use a lot of AI. So for the moment, my student mostly use AI for the codes,
For code, yeah.
for coding.
Yeah, yeah,
So they use in particular Claude.
yeah.
For the mathematics, I'm not completely confident in ChatGPT or any AI tool. But maybe it will improve. But so I think that of course, if you have some idea of the proof, or if you can give some good prompt, okay, it can help you to okay to okay to suggest you some idea okay how to find the proof. But okay, of course you need to master all the tools and to check, because I already found some mistake in some proof, so I will not trust completely AI for doing the math and the theorem.
But
I
if the
think that,
proof was say they said they put the proof through lean, for instance, would you trust the results? They say like it went through lean, and lean says that it's correct.
I don't know. So if it says no, so I will not. If it says correct, I will not trust. I will check by myself.
You still check by
I
yourself,
will try check by myself. Yes, yes.
even if
So
lean says
so
it's correct.
yes, to check is correct. So I will not try. Okay, it's not because the AI says that it's correct that for me it's correct. So so maybe it's okay. I will not find by myself the proof. So I
Yeah.
can I can ask him, okay, how can I okay, what tools can I use? And so he suggests me a proof. So maybe okay, it helped me, and then it helped me if okay, it's a good idea, good track to follow. But of course, I will always check if all the arguments are correct.
Because Terence Tao argues that because of he will trust the result of lean, that now he can write papers with random mathematicians, people he doesn't know, because he doesn't need
Yes, so maybe
to
he
check
has
their
a
proofs. But
maybe he has a better AI tool than me for the moment. I
because he
only
said
have the
because well, I mean his argument was interesting. He said before he could write papers only with 2 or 3 people because he know that these people are trustworthy, he will trust the results. But now he said that because of thanks to Lean, he can like write papers with like anyone, and then so can write a paper with hundreds of co-authors, and as
yes.
long as it goes through Lean, he will trust the results. But
That's true. So, and by the way, in fact, also now I know that LLM are also used to review paper. So this
yeah,
means that
yeah,
more and more, for example, in uh, NeurIPS or ICML, they use
yes,
LLM to review. I mean,
yes,
preliminary.
yeah, yeah,
So
yeah. It's as a
I don't know.
referee, right? Yes, yeah, yeah,
Yeah,
yeah.
so at some point, maybe it will replace referees, human referees.
Yes, yeah, yeah. I think it makes sense. I think yesterday I was hearing a talk and they were saying that because the variance of referee, because it's very difficult to find referees, for these
Exactly,
conferences.
exactly.
So some are very good, but some are very bad. So there's a huge variance. So at least the LLM gives a bit of kind of so it's not great, but it's not that bad, right? So it's kind of maybe as a
Yeah,
first
yeah. So at least
step.
I checked. So in fact,
Yeah.
it's and now to be honest, I know that many people use many referees use LLM to do their own report.
Yes,
So
yeah,
it's
yeah. Okay.
but of course, yes, it's but I think it
Yeah,
also gives you an idea whether the paper is correct or not.
yeah.
So
Not
if
only that, but now there's a trend, I think, in the archive, many papers are written by AI now, right? So now
yes,
for
yes, yes. So I mean, not completely,
not completely, but at least
but
with
yes,
a
yes,
lot
for
of help
sure.
from AI.
I think, or at least for the reduction of the
Yes.
introduction, the reference, but yes, probably many more and more papers will be written at least partially by AI. So this
It's
means
very
that
useful. It's also useful for non-native English speaker, non-native
yeah,
speakers, right?
yes, it improves. Yes, so now you can write an introduction and outside in just 1 minute instead of half day. Yes, so and also the consequence that now people and PhD students have become more productive. So
Yes.
before, yes, probably a PhD you need three years to complete your PhD.
Yeah.
Now probably one you can divide by at least half the length
Really?
of the PhD thesis.
Ah,
Yeah, probably yes, because
yeah.
now you can produce a paper maybe just in 1 month or 2 months. So I think now we will see that, or maybe we can ask now for PhD to students to produce at least 5 papers or 5, 6 papers before
This
you can
PhD. And so
decide. That's
the
the
bar is
point of
higher now. So
yes.
before people
The
pass was
level
enough.
requirements may come higher, or you can diminish, you can decrease the length of the PhD.
Okay. You can get a PhD in 1 year, for instance, instead of 3 years or
Yeah,
4 years.
because now
Yeah.
you see that I already I have already been contacted by high school students in
Yeah.
US, so who read all my papers,
Yeah.
and so I don't know at which point they are able to understand,
Yeah.
but they read my paper and they ask me if they can do a project, they can do research. Okay, they are just in high school.
Wow.
So it's now I see even high school, you will see more and more high school students doing research. Of
Yeah,
course,
because
with the
also
help of AI.
because they can also ask the AI to explain them, so papers, a concept, and
Yes,
so
yes,
on, right?
exactly.
So then
Yes,
they
yes.
can learn. So people who are very
Yeah, yeah,
motivated and smart, they can learn by themselves. Yeah. Yeah.
yeah. The number sense.
Very good.
It's,
I don't see any questions, but I mean you can always reach Professor Huyên by email or reach him like these high school students if you have any questions. But thank you very much. It was very interesting, and I really salute your efforts to make it accessible, because we read the paper. It's a bit technical.
yeah, yeah. So
But
here
the presentation was great.
I
So
try to reduce as
yeah,
most as possible the
yes,
mathematical formula. So just
yeah,
because I'm aware that the audience is
yes,
not the audience that I have in general. So
yes.
and so of course, so I think that you put online, right? This slide. So
Yes, yes, yeah, yeah, yeah. I'll put it online. It'll be on YouTube today or tomorrow or tomorrow.
okay,
Okay,
okay.
so thank you very much, and I'll see you soon,
I see
probably
you
in
soon
Paris. Okay.
in Paris. Bye
Okay.
bye.
Bye-bye.